Hi everybody. This lesson on areas of regular polygons is probably it's the hardest lesson of the chapter. And so this might be a video that you're watching because you missed that day, or maybe you're just coming back and watching a few of these examples to help you through your homework. Either way, I'm going to go through a lot of examples and hopefully you find something that helps. To start with, when we look at a regular polygon, remember that means all the sides are the same, or all congruent, and all the angles are congruent. It's just your typical polygon. When you think of a stop sign, that's a regular octagon. This is an example of a regular hexagon. The parts of a regular hexagon have similar parts to what a circle would have. We have the center of the regular polygon, and then we have the radius, which seems weird to have a radius in this, but the radius goes to the corner, to the vertex of the hexagon, just like it would be a radius of the circle that hit all of the vertices. All right, an apothem, that's probably a new word for you. The apothem is the segment that comes from the center straight down, perpendicular to a side. And so because this is a regular polygon, this is always going to end up perpendicular. It's going to hit right at the midpoint of these two sides. What happens when you look at the apothem and the radius within your polygon, you end up getting a right triangle. And we do a lot of our right triangle properties with these problems. On this page, what we want to do is we want to look at some angle measurements, because we're going to be looking at a lot of angles and doing, like I said, we're going to end up with some 30, 60, 90 triangles, or we might do SOHCAHTOA, all kinds of things. We look at this, and the first thing we want to do is we want to look at the central angle. The central angle would be this angle right here, or this angle, and these are all the same because it's a regular polygon. In this problem, we're trying to find the measure of angle 1, the measure of angle 2, and the measure of angle 3. If you look at that, the measure of angle 1 is the central angle. It's right here. It just happens to be in this triangle over here. To find that central angle, you're going to have to remember that it's 360 degrees all the way around. So what I'm going to do is I'm going to take 360 degrees and I'm going to divide it by how many of these central angles there are. Since it's a pentagon, there's 5 of them. I'm going to type in you're going to want your calculator handy. If you don't have it out handy, grab it right now. The measure of angle 1 then is going to be 360 divided by 5. It ends up being 72 degrees. The measure of angle 2, if you'll look at where that's located, it's not this full central angle, it's the angle after the apothem got dropped. And in the same way that apothem splits the side into 2 equal parts, it also is going to bisect this angle up here. This angle is going to be the same as this angle. I just need to take my 72 degrees and divide it by 2. 72 divided by 2 is 36 degrees. And then the other angle that we have is angle 3, which is this angle right here. Now there's different ways to do this. We did have a whole chapter where we talked about like the interior angle, and we could find that interior angle in a pentagon. But it might be just easier. We already know angle 2 is 36, and we have this 90 degree angle. We really could just subtract those from 180 because it created this little triangle here. If you subtract 90 and then subtract 36, you're going to end up with 54 degrees for angle 3. All right, now my intention here, remember this little sign here means that it's time for you to try. So why don't you pause the video, see if you can figure out angle 1, 2, and 3. Looking at this, sometimes we get, I don't know if it's lazy, but we don't draw out the whole pentagon or the whole polygon. So this, they haven't drawn the whole thing. There'd be more sides to this, but I can see right here that I've drawn half of it, and there's 4, so this must be an octagon. So keep that in mind when you're doing that. This is an octagon. Go find the measure of angle 1, 2, and 3. All right, did I tell you to pause the video? I was supposed to tell you that. Anytime I have you go do something, you need to pause the video because I'm not going to wait throughout the whole video for you to do that. All right, angle 1 is my central angle. I'm going to take 360 and I'm going to divide it by 8. It comes out nice to a 45 degree angle. But then when you drop that apothem, right here, that's going to split that 45-degree angle into a not so nice number, 22.5 degrees. And lastly, I'm going to have measure of angle 3, and same deal. I'm going to look at just the little triangle that was formed. I know angle 2 is 22.5. I know that I have a 90. I'm just going to subtract those from from 180, and I end up at 67.5 for that angle measurement. Now we're going to use that idea as we move forward. We're going to look for the area of a regular polygon, and that's pretty much all we're doing today. Find the area. Now, if you have a regular polygon, this is just another piece of a polygon, but it's broken down into all of these triangles, and all these triangles would be the same. It's in yellow here. All of these are going to be the same triangle, so it just depends on, if I could find the area of this triangle, I could just multiply it by how many there are, and I'd have the area. And we know how to find the area of a triangle. That's just 1/2 base times height. In this particular picture, the base is really the side length of the regular polygon. So instead of calling it a B, we're going to call it an S for the side length. Oftentimes we'll know what the side length of the polygon is. Okay, the height of it is really this measurement here, which we think of as the height of the triangle, but in the regular polygon, remember, from the center perpendicular to the side, that's called the apothem. I'm going to call it A, and I'm going to put it in for my height. Now that's the area of just my yellow triangle. Then I'm going to multiply it by however many sides there are. If it was an octagon, I'd multiply it by 8, for instance. That can vary, so I'm just going to put multiply by number of sides. Because what I'm really looking for here is sort of a pattern of something to simplify this up. And here's what it is. If you take this side, it's this side measurement right here, and I multiply it by the number of sides, and remember that the order that you multiply doesn't matter. I'm taking a 1/2 times this, times this, times this. I'm picking out a couple. I'm going to multiply in a different order. The side times the number of sides. If you take this side measurement and multiply it by however many sides there are, what are you actually finding on that? Did you see perimeter? Thought you did. That's the perimeter of your polygon. So I'm going to clean this up right now. It's area equals 1/2, and I'm going to put my apothem next, and then the side times the number of sides is the perimeter of our regular polygon. That is the area formula that we use to find the area of any regular polygon. Okay, so I put this slide in there just so you had a nice clean slide of the formula that we're going to use right here. And then I also threw in the special right triangles in case you maybe, I don't know, need a little review of that. Hopefully, no, you've got it down pat maybe. All right, so those are your special right triangles, and then of course sometimes you'll have to do SOHCAHTOA if it's not a special triangle. Now we're going to be using, I had mentioned earlier, we're going to use some special right triangles, we're going to do some SOHCAHTOA. Let's look at why we would be doing that. In this first example here, I have a square. It's a type of regular polygon. It's just a 4-sided regular polygon. And what I've done here is I've dropped the apothem to the square, and I've dropped the radius to the square. And what happens, if you think about it, 360 divided by 4 is 90. And when I drop that apothem, that 90 turns into a 45. That's 90. Hey, we've got ourselves a 45, 45, 90. When we're trying to do the area formula for a regular polygon, well, I need to know the apothem. That's part of it. I need to know this side length so that I can do the perimeter. You may end up having to use what you know about special right triangles to be able to find those missing parts. All right, this next example is a hexagon. You take 360, divide by 6. That's 60 degrees. But when you drop the apothem, the 60 turns into a 30, and what do you know? You've got yourself a 30, 60, 90. And again, these are the key parts for our formula. If they give us one thing, we should be able to find the others. All right, last one, equilateral triangle. 3 sides, so I take 360, divide by 3, and this central angle ends up being 120. But when I drop the apothem, now the central angle splits into equal parts, so this is a 60. I have another 30, 60, 90, but you can see it's oriented differently than it is up here. So now the apothem is the short leg, whereas up here the apothem was the long leg. All right, so these are the 3 that actually come out nice to where we can quickly use special right triangles. If it's not one of these, when we do the whole 360, divide by how many sides there are, and then split it in half because of this, like that one we did that was an octagon, it had a 22.5. That is not a special value for a triangle. And so if that's the case, we'll end up having to use SOHCAHTOA to work on that problem. All right, let's try some. Like I said, we are going to power through a bunch here. Let me move this real quick. Give us some more space to work. All right, so we're going to start off, and I'm always going to start with my formula. Area equals 1/2 the apothem times the perimeter. Sometimes they're going to give you exactly what you need. Sometimes you're going to have to do a little bit more work. So the apothem, yep, that was given to me. The perimeter, well, I can find it pretty easily because I see that the side is 8. And what do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a decagon. So I could find the perimeter. It's 8 times 10. I think I have what I need. Let's just start filling in numbers. Area equals 1/2 the apothem, 12.3, times the perimeter, which is 8 times 10. I'm going to put in 80, and then we're just going to our calculator on these. I'm going to try to do some different things. The directions, sometimes we'll ask you to round to the nearest tenth. Sometimes they're going to say leave your answer exact, which means if you have like a square root of 3 somewhere in there, they want you to leave that square root of 3. Don't type it in your calculator. This one had a decimal. I'm guessing they would want a decimal on this. I'm just going to go 0.5 times 12.3 times 80 gets me 492. The area of this decagon is 492, and then its area, so it's going to be inches squared. Okay, enjoy that problem. The rest aren't that easy. Let's try another example here. This time I've decided I'm going to go ahead and put in there, sometimes we're going to do it exact, sometimes a decimal. This one we're going to try to keep exact. The other thing I might make note of, I'm not always positive that these slides come in the right order, so if you find that I'm doing a problem and it doesn't match your notes, maybe just look ahead a little bit, you'll find this problem. And hopefully there's not a lot of that. But all right, so starting off, I'm going to go ahead and do my area formula. Area is equal to 1/2 the apothem times the perimeter. Looking at my picture, they don't give me the apothem at all. But they do give me a side length, which would lead me to my perimeter. That means I'm going to have to draw the triangle. So I'm going to start here with the center. I'm going to draw in a radius, and then I'm going to draw in another radius. And what I'm looking for is what that central angle is. So 360 divided by 6 sides, that's a 60-degree angle. But when I drop the apothem, that 60-degree angle turns into a 30. And the next thing you know, you got yourself a 30, 60, 90 triangle here. So I'm looking at this triangle when I do this problem. In that triangle, what I know is that this side length was 3 right here. So that means this side length is 3, and this little piece that I want is half of that. Now when they say exact, they're going to want fractions, not decimals. So I'm going to go not 1.5, but I'm going to call it 3/2. And then I go to my special right triangles. That's the short leg. Long leg is going to be 3/2 root 3. That's your apothem, which is what you needed. And I could write the radius, but I really don't need to because it's not really part of my formula. Let's go over here to our formula then, and let's start filling in. 1/2 the apothem, and it might be good to start getting in the habit of writing this a better way. Instead of 3/2 root 3, they typically will take the root 3, because it's like a root 3 over 1, so they put it up on top. So it would look like this, probably would be a better way to write that. Times the perimeter, well, my side length was 3, take it times 6 sides, I've got 18, and just because I know I'm going to have to do some reducing, I'm going to go ahead and call that 18 over 1. Trying to keep everything exact, let's start reducing. This 2, let's change colors because it might get cluttery. This 2 and this 18 can reduce. That would turn into a 9. And then sometimes there's other stuff that you can reduce. Doesn't look like I have it here. So then my final answer, if I multiply across on the top, is going to be a 27 root 3 over 2. And that would be my exact answer. It's measured in feet, so I go feet squared. That is the area of that hexagon. All right, let's try another one. This one I'm going to round off. Let's do one where you have to round it off, and it's another hexagon, but they're giving me something different. This time they're giving me the apothem measurement. And what I'm missing then is the perimeter, and so that's what I'm going to have to work on. Now you're going to start to get the hang of it. I have that whole slide of which ones are the special ones, but I'll walk us through it here because it's not necessarily going to be something you remember on your test, so let's go through it. I draw in that central angle, and since there's 6 of them, it's 360 divided by 6. That's 60. Drop the apothem, it's now 30. And so I have myself a 30, 60, 90 triangle right here. Of that, I actually know my apothem. It's 4 root 3. So over here, when I'm thinking through my formula, I'd have 4 root 3. I guess if I'm going decimal, I don't really have to write this as a fraction. I was going to put that over 1, but I guess I don't have to since I'm going decimal. All right, times the perimeter. Okay, let's see. This is 4 root 3, which it's going to be important when you're drawing these that you make this look like a regular polygon. It looks like this. If you make it kind of flat looking, which a lot of people do, this long leg starts to look like it might be the short leg. So be careful with that. In a hexagon, this apothem is the long leg. It's 4 root 3. What do you think the short leg should be? 4. That's right. You were right. Good. All right. And if I wanted to find the radius, I know it would be 8, but I don't really need it. What I need is the perimeter. So what happens here is if this little leg is 4, all the way across would be 8. And then I have 6 of those sides. So 8 times 6 is 48. And then I'm just going to go to my calculator. Now, one of the things you're going to have to learn about doing the calculator on Math Excel is that Math Excel is super picky about decimal places. And if you end up having to do, this one's going to be easy because I'm just going to go left to right in my calculator. But you're going to want to always leave numerous decimal places, and you don't round to the tenths until your final answer. So if you were doing this in parts and you had this little thing over here and this little thing over here, keep those like to the thousandths. Keep 3 decimal places. And then after you've merged everything together, then you can go to the tenths place. This one, let me see what I got. And it's good also to, you can sure shorten your work if you do a little bit of mental math. And I'm going to kind of train you to do that because I think it's good for you to know some mental math anyway. Remember how the order of these does not matter? I can multiply in any order I want. So instead of taking and typing in 1/2 times 4 root 3 times 48, I can go ahead and take the 1/2 times something. And I'm going to take it times the 48. Well, and you could just easily take 1/2 of the 4 root 3. That'd be 2 root 3. I'm going to go 1/2 of 48. That's 24. So that takes care of that. I'm just going to take 24 times 4 root 3. Just a shortcut to hurry up what you're typing in the calculator because sometimes that doesn't come out very nice. All right, I got an area of 166.27, so I'm going to go 0.3. And this one didn't have any units. I could write units squared, I suppose. All right, back to exact. On this one, we're going to find the area. Now we're going to switch it up. Not a hexagon. We've got ourselves an equilateral triangle. If I come up here and do 1/2 AP. I do not know the apothem, but if I know a side, I can figure out the perimeter. So I'm going to come over here and I'm going to draw this in. Remember, you draw in the 2 radii. That's 360 divided by 3. That's 120. drop the apothem. Now it's 60, get yourself to 30, 60, 90. But the apothem is our short leg. All right. This whole side over here is 8, but that means this is also 8, which means this leg, this long leg, is going to have to be 4. Now this is going to take a little bit more work because that's not as nice. The long leg is 4. I have to take the long leg and divide it by root 3 to get the apothem. So 4 divided by root 3. And then you have to rationalize that. Root 3 of root 3. I end up at 4 root 3 over 3. That's the apothem measurement. That's pretty ugly. All right, let's go over here and write it in. The apothem is 4 root 3 over 3. And the perimeter, if each side is 8, 8 times 3 sides would be a 24. Since I'm leaving it exact, I'm going to put it over 1 because I got some fractions to reduce. 3 and 24 can reduce. 2 and 4 can reduce. All right, so at that point, everything's out of the denominator, and I have everything left in my numerator. It's a 2 times an 8. That's a 16 root 3 inches squared, and that's how you would enter it in Math Excel, just 16 root 3. Here's another one, going back to, or keeping it exact, but I've got a square, and they've given me the radius. Always start with my area formula. Again, don't have the apothem. This time I don't have the perimeter or a side or anything either. They really have given me the least helpful thing. They gave me the radius. All right, I'm going to go ahead and draw that radius and another radius and figure out what this central angle is. 360 divided by 4. That's going to make that actually a 90-degree angle. But when I drop it, it turns into a 45. Okay. So I have a 45, 45, 90. That's the first time I had one of those. Now, this is what was 6. Just to clarify, because that 6 is caught up in the middle of everything now. It was the hypotenuse that was 6. Do you remember how do you get from your hypotenuse to your leg in a 45, 45, 90? Why, yes, you do divide by root 2. You are brilliant today. 6 root 2 over 2, that actually reduces, so my legs are going to be 3 root 2. Now my legs are both important parts. The 3 root 2 is going to be this leg, which is my apothem, but it is also this partial side of the square. I'm going exact. I'm going to go ahead and write 3 root 2 on top. I don't know, maybe there'll be some reducing or something I can do. Okay, the perimeter. Well, the little piece here is 3 root 2, which means altogether this is 6 root 2. It's twice that. And 6 root 2 times 4 sides is 24 root 2. Up here then I have 24 root 2. And then I'm ready to reduce. The 2 and the 24 can reduce. And then this is actually going to multiply kind of nicely, because if you look at what you have this root 2 getting multiplied by this other root 2. And a root 2 times a root 2, remember, is just 2. I'm going to lose the radical on this problem. That's just 2. Times the 12, that's 24, times the 3. 24 times 3, 72. So this whole thing just came out nice. It's just 72, which is easy to make exact then. There's your final answer. All right, here's an equilateral triangle. Again, the radius was given to you, the least helpful thing. If you draw in another radius, so you have these 2 radii. Do you remember what happens on this one? You start to do enough of them, you start to remember. Maybe we're not there yet. But it's 360 divided by 3. That's 120. Drop the apothem. Now it's a 60. We have ourselves a 30, 60, 90 triangle right here. And the apothem is our short leg. And I said that they gave us the radius, which is least helpful, but it's not too bad. In this nice 30, 60, 90, that's the hypotenuse, and that's easy to divide by 2. That gets me an apothem of 2 and a long leg of 2 root 3. Let's come over here and start up our formula and fill in everything that we can. 1/2. The apothem, this time I'm going to tenths place, so I'm not going to worry about the reducing. I'm just going to write this straight across. It's 1/2 times 2, that's the apothem, times, now here's the tricky part, 2 root 3 is this piece, so the whole length would have to be twice that. We'd call that 4 root 3. And then 4 root 3 times 3 sides, 12 root 3. Right. Like I told you last time, it's nice to be doing some mental math. This 1/2 times 2, that's just going to go away. So I'm left with the answer, 12 root 3. However, they want that as a decimal, so then I would go ahead and type that in the calculator, 12 times the square root of 3. And I get 20.78, and if I'm going to the tenths, that's going to be 20.8 square inches. All right, I hope you're getting the hang of it. We got a few more. Here we have a pentagon. And when I draw in the other radius here, and then I do 360, and I divide it by 5. And for the first time, 360 divided by 5 happens to be 72. And when I drop the apothem, that 72 splits into a 36, and that is not a special right triangle. All right, that means SOHCAHTOA, which makes sense. Then we're going to be rounding this to the tenths because there's not really a way to do SOHCAHTOA and keep it exact in any way. It's always going to be a decimal. What you're going to have to do is you're going to have to pull this right triangle out of here that we have. And you only know the 36-degree angle, you know that, and you know the side that's a 10. To do your formula, A equals 1/2 AP. A is the apothem. We do not have that. Let's look for that. I'm going to come down here and look at this. This is 36, this is 10, and this is, I'm going to call it A, I guess, because it's my apothem. And you have to decide, are you using sine, cosine, or tangent here? This is a good review to do this before our final. With this angle, 10 is my hypotenuse. It's across from that right angle. A is adjacent. It's right next to it. Adjacent and hypotenuse. That's cosine. So I'm going to do cosine of my 36-degree angle equals A over 10, the hypotenuse. All right, this is the nice scenario because I get to just multiply both sides times 10. And then I'm going to type in my calculator 10 times the cosine of 36. And I get A to equal 8.09. So I'm going to have that I can go plug in. But I'm not quite done. I got the apothem, but I got to work on my perimeter. And my perimeter is going to actually come from this. Okay, so looking at my triangle again, I'm going to work in a different color this time. So this is going to help me find my perimeter. So now I'll call that X, I guess. Now I'm going to look at this triangle a different way. I'm still going to use the 10, but now I'm looking for this side, and that's a 36. Now I've got opposite and hypotenuse. That's sine. Type in my calculator 10 times the sine of 36. And I get X to equal 5. And this is what I was talking about. It says round to the tenths, but you leave more decimals there until the end. The last time I went 09 because it split very nicely. The next number was a 0. But here I'm going to write just a few more. It's 5.878, I guess is what that would round to. And now I'm going to come up here and fill in my numbers. Let's go ahead and circle that because that's actually, let me undo that. That's actually not what I need. X is really just this piece, and I need the full perimeter. Let's look at what I have to do with my 5.878. I need to, first of all, double it so I can get that full length, and then I'm going to take it times 5 to get all the sides. So times 2 times 5, or you really could just take it times 10. That does it too. Which actually you could do a times 10 then in your head, but down here I'm going to write perimeter equals 58.779 is what that would round to. Let's grab that and go plug it in here for the perimeter. And now I have area equals 1/2 8.09 times 58.779. Are you doing this with me, or are you just waiting on me? I'm kind of slow. You should do it yourself, probably. A equals 237 rounded to the nearest tenth, 0.8. No units on that one, so I could write units squared if I wanted. But all right, so a little bit more work on that because, well, a couple reasons. SOHCAHTOA is a little bit more work. Plus, they gave us the radius, which wasn't super helpful. Let's do a few that are like this. All right, again, finding the area, round to the tenths. This one happens to be a 1, 2, 3, 4, 5, 6, 7, 8 octagon. All right, if I put the 2 radii in there, and I do 360 divided by 8. I've done it a few times. It's 45, if you didn't know. Okay. But more importantly, when I drop the apothem, it's not 45 anymore. Now it's that 22.5 weird number. 22.5 is that angle. And I'm going to look at this. I know that that's But I do know that the full side length is 6, so this little half side length that I want is going to be 3. Now, remembering that I'm going to have the apothem at some point, I think that's going to be the thing I need to find. So let's put a little A for apothem. And I'm going to use this 3. What do you think? Is that going to be sine, cosine, or tangent? Tangent it is. Tangent of 18 degrees is equal to opposite over adjacent. Now this is a little bit weird. It doesn't work as nice. This is the one where you have to multiply both sides times the A to get rid of your fraction. So now you have A times the tangent of 18 equals 3. And where you have to come back and you have to divide by the tangent of 18. That's why I kind of wrote this up here. I knew it was going to take me some work. Now, some of you have done this enough times, you can kind of see and do that in your head. That's fine. I just know that my apothem is going to have to be 3 divided by the tangent of 18. And putting several decimal places in there. Oh, notice that it's wanting it to the hundredths on this one, so I'm going to definitely put several decimal places. It would go like that, would be the apothem. Right? I think I can do my formula now. A equals 1/2 the apothem times the perimeter. Okay, 1/2. The apothem is 9.2331. And the perimeter, let's look at that. Each side is 6 units. And there's 10 sides. That's 60. All right. If you wanted to do middle math, it wouldn't be very easy to do half of this 9.233, but I could do half of 60. Half of 60 is 30, so I'm going to type 30 times 9.2331 equals, and my area formula, to the hundred. Ooh, wow, look at that. To the hundredths. I have I guess to the hundredths, it's going to be 276.99. Now, if that, and my next number happens to be a 3. If it was bigger, I might have had to round that up, and it would have been 277.00. So, just a fun little thing there. All right. There's our area. All right. That's a lot of them. Hope it helped. Hope you can find one that works for you.